Good morning, students. Hopefully the audio is coming across. Can everyone hear me? Liliana, you usually let me know if you can hear me.
Yeah, we can hear you.
Yeah, we can
Thank
hear
you.
you.
Thank you. I know you get tired of this, but I really it's important. I mean, the visual is good, but we have to have the audio and just making sure that the technology is working as we need it to be. Now, what we're going to do today is continue with the integration review. That is the techniques that we have learned to this point. Usually a lot of them have to do with the techniques you learned in Calculus 1, and then of course the few new techniques that we learned with the inverse trig functions. So we want to review some of those topics and just kind of get ourselves back into the mode of doing antiderivatives. And then when we complete that, I want to go ahead and start talking about integration by parts. The applications are important, and so as we learn more techniques of integration, you can actually broaden the number of applications that you can do, because of course what results in the application is an integral, and then of course your ability to do it depends on the techniques that you actually have at this point. So again, I think you're going to find this next series of lectures to be very stimulating, in the sense that you're going to really broaden what you can do in terms of antiderivatives. So let's go ahead and get started with that. Now, the first problem I have here, like I say, we're going to do some review examples and basically cover ideas that you're aware of. And in some cases, you may think, oh, this is really very simple, and that's good. And in other cases, you might think, well, I need to review this. I learned this last term, or Professor Ron's talked about this, but I'm not always sure what he means by table ready. So let's go ahead and look at several of these. Now, again, this is meant to be refresher review type stuff. So when you do these problems, don't worry that everything doesn't come back to you at once. Just take your time to work through the process. Now, when we look at a problem like this, we think about a calculus 1 integral, because it looks like we have some form of the derivative of cosine. So this is another add 1 divided by the new power. So what we want to do first is make it a little bit more user friendly. Lots of you find that when you do these problems, you see a form that you recognize, and so you don't worry about writing with negative powers or whatever. But I find it very useful to do that. It cuts down on the amount of work we have to do in our head. Now, of course, we've got the sign here that just comes along in the numerator. And so what we want to think about is a table ready form, because we see that we have the cosine raised to a power. And so when we think of cosine, we just kind of think about a u substitution. And a lot of times we don't even write this down because it's really simple, but this is a good way just to remind ourselves how we make things table ready. So the differential here will be the negative sine x dx. So the thing that makes most of our integrals work is the fact that we can utilize the chain rule. And if we didn't have this, we have to come up with another form, like maybe the inverse trig forms, but we're still using the same process. So now this just says we need a negative. So what we're going to do is we're going to put in the negative. So we can just write the negative sine x dx. And then, of course, compensate for it, because we want to write an integral that is equivalent to this one. But now we look at this and say this is table ready. We have our du, we have our u raised to a power. So we call this table ready. For instance, as we do more integration techniques, we'll develop some integral forms that will actually end up in a table. And all of these are in a table in your basic forms. So now we add 1 divided by the new power. So we have the negative, which is already there. We add 1 to negative 1/2 to get 1/2, but then we divide by that. So that's multiplication by 2. So remember, our favorite form is add 1, divide by the new power to give us the 1/2. Division by 1/2 is multiplication by 2. And then we're good to go. Now, one thing we want to do here is remember that this is an indefinite integral, and a lot of the problems we're going to be doing will be indefinite integrals. So we always have to remember the arbitrary constant. And remember, in the WebAssign, the directions are to use an uppercase C. If that ever changes, you will be directed to do that, but it's always an uppercase C. Now, of course, if you wanted, you could just write this with the radical notation. You can always dress up your antiderivative. You can factor it. You can get common denominators, things like that. That's not always required because WebAssign is very flexible. But there will be times when they might, give you some type of formatting directive. But normally students find this to be very much a personal choice to rewrite the integrand. And we will do it when it's serving us. For instance, when you look in your engineering books and science books, your formulas always look very nice, neat, and clean. And that's what we want to try to work towards. Now, let's try some other examples. All I've done is pick some problems from your WebAssign and then some in your textbook, just to give you a good variety of problems. So again, we're not really learning any new technique here. We're just trying to remind ourselves of what we already know. So now when we look at a problem like this, this is a common occurrence in trigonometry. So if we were doing an identity proof, the first thing that would come to mind would be a conjugate method. Now, the problem here, we're going to have a method later on that deals with rational expressions of cosine and sine, ladies and gentlemen, and that will be called the Weierstrass substitution. But it is complicated, and so if we can avoid it, we try to do that. So of course, what we're going to do here is look at a conjugate method. We'll do the sum of this, cosine plus 1, and multiply and divide by that and see if that helps us out. Doesn't matter what you try. If it doesn't work, try something else. That's the art of doing mathematics. So we'll do the conjugate method. So we're getting a break from all of the symbolic computation with the arithmetic. So now notice here in the denominator, we have a difference of 2 squares, and in the numerator, we just have the conjugate. So let's go ahead and write that. And then of course, downstairs, we have cosine squared minus 1, the outer and the inner terms obviously absorbing. So I really want you to take a lot of time to review these, even though you may feel that you already know it. Please go through this thoroughly and really shore up the confidence that you have with doing antiderivatives. We want to make sure that all of this is very comfortable for you. Now we look and say, okay, this is the fundamental identity here. This is the negative of sine squared. It's just flipped around. So if you like, we have cosine theta plus 1. And then I'm going to go ahead and move the sine squared, the negative, outside, just to kind of get it out of the way. That way we have the negative sine squared here, but I'm going to remove it to the outside of the integral sign, just using linearity. And now when you look at this, you're thinking, okay, this is a rational expression in sine and cosine that we can reduce using our basic trig identity. So let's do that. So we'll write cosine theta, and I'm going to go ahead and break up the sine into two pieces. That way it's easy for you to see the identities. Lots of times students, you know, you get a little bit uneasy with this because we do trig, then we leave it alone, then we do trig, and so it's not something we do every day. So now when you look at this, we can see we have the cosine over sine, which is the cotangent, and we have the 1 over sine, which is the cosecant. So we can go ahead and write that. We know about that. So we have cosecant theta, cotangent theta. And then of course here we have 1 over sine squared, which is cosecant squared. Now, when you look at this and you think, okay, well, are these integrals that we know, or these things that we know when we do our calculus? Notice the derivative of the, let me just write this up here. Let's do a little recall. Well, I guess we need the right side here. Recall. The derivative with respect to x of the cotangent is the negative cosecant squared. And so now what we can do, if you like, we can go ahead and run in the negative here to get the antiderivative. So this implies that the integral of the cosecant squared will just be the negative cotangent. Right there. So that's something you learned in Cal 1, but again, this is probably a little bit rusty. So now let's go ahead and break this up. We have the negative of cosecant theta cotangent, just so you can see the integral separately. You don't have to do all these extra steps, but it's good to write them out just to check your work. So now, if you remember, the antiderivative of the cosecant cotangent is the negative cosecant. So we're going to get the negative of the negative. So negative cosecant. And then we have the negative of the negative cotangent. And then we can add our arbitrary constant. We're not being sloppy by waiting to the end to add this. We just, you know, get it, don't mix it up until we need it. And then of course, these negatives absorb and we get cosecant theta plus cotangent theta plus a constant. Now, again, the best way to remember these basic integral formulas from your Calculus 1 class is just to think about the derivatives. Again, the derivative of the cosecant is the negative cosecant cotangent. So that's how we get this particular form here. So it's just like what I've done here. So when you make your note cards and you go back through the lectures, just make a comment about some of these derivatives. So just as a little extra here, let me go ahead and remind you of that. We just used it. I spoke it, but let me just write it. And you can use the chain rule if you want. I'm just using X here. Now, let me try something here. Let me do this. Let me write it in a correct way, actually. Let me just put the same thing I've done here, and then I'll do the other ones. Get the parallel one to this. Just as review. So the derivative of a tangent is the secant squared. So this will give us this integral, which we'll use. Now, when you think about what we did at this part here, when we think about the actual integrals here, let me just go ahead and write these down. There's that one. And then the corresponding one, let me get rid of all this stuff here. And then the corresponding one here that we used right here. These are all standard forms that are easy to forget using the derivatives backwards. So put all of these formulas on a note card to remind yourself exactly what's going on here. These are important formulas. They're really simple. They're very simple formulas, but they just don't always stick. And so remind yourself how you actually do these. And again, we kind of started the ball rolling here, and then we see that we will use these simple integrals all through our work. So we need to refresh ourselves of them. So I'll take an opportunity to write some of these things down when it will be helpful to us. Okay, let's look at another one. So again, like I say, you have your own methods. You can use your integral tables in the book, or you can just make some note cards. So now I want to do one that is similar to the one we just did, because it's a good technique, and you're gonna think, well, this is the same problem. It's similar but not the same, but the technique is really good. So here's another example, and it's written this way. This is out of your book. So we have 2 upstairs, and we have a 3 secant x minus 1 dx. It's like that. Now you're thinking, this is very similar to the last one, and if we like, we can use some techniques to rewrite this to make it easy and make it basically look like the last one. Some students will say, well, should we use the secant and the conjugate, or would it be easier just to kind of convert things to the cosine and make it look like the last problem? Well, for most students, I find that it's probably a little easier to work with the sines and the cosines, but that is completely up to you. So what I'm going to do first is I'm going to factor the 2/3. And then what you can do, you could do the conjugate with the secant x plus 1, or you could do this, just to rewrite it. So again, remember, we're going to use some trig identities, and of course, these are valid where they're defined. And so now the 1 over cosine is replacing the secant, and now we can multiply and divide by the cosine. So let's do that. So this is going to look similar to the last one, but I'll include all the steps here. I want you to be comfortable with this. So we'll just do our little convenient one here. So now this may look just a little bit more convenient, and then we can apply the conjugate method. Again, you can start from the very beginning and go this way, but I think this might be easier for you. So now we have cosine x in the numerator. And then when you look at this, the cosines absorb, so we get 1 minus cosine. So think about this just distributing the cosine. So this gives us 1 minus cosine x. dx. So what I've done here is completely up to you. You can conjugate this and move the problem forward that way. But I thought about this and, considered that this might be a little bit more straightforward. So now this looks very similar to the previous problem. So now we'll apply the conjugate method. Again, we have a rational expression of cosines, which we can't do much with unless we rewrite it. So we want to use another identity. So we'll do 1 plus cosine x, which we did similar to the last problem. So again, the conjugate method, and just notice downstairs, we have a difference of 2 squares. So now, again, we have the 1 minus the cosine squared, the outer and the inner absorbing. So this gives us 1 minus cosine squared. And then upstairs, we get, again, distributive law, we get cosine plus cosine squared. I'm glad this problem has x's in it, but I always like to write x's, but we use what WebAssign gives us. We don't make it up. We have to follow the WebAssign. It's smart artificial intelligence at our disposal. So now when we look at this, of course, now we have the fundamental identity, the sine squared. So let's go ahead and write that. Again, you can put more or fewer steps in these problems depending on how confident you are, but I want to make sure that the steps are clear to you. I get lots of questions from you about integration, so I want to make sure that this is good. Now we're at the same place that we were with the last one. That is, we're at this point, so we're just going to break it up like we did here. So let's break up this into 2 pieces. So we'll have a cosine x. So this looks very similar to the last one, sine x, then plus cosine squared x over sine squared. So again, it might be more comfortable with the sines and the cosines. Again, that's a personal choice. So now we can see we've got the same thing going on again, but just with a little bit of difference. Notice here, we have the cotangent, cosecant, like the last problem, but here we have the cotangent squared. So we have cosecant, the 1 over the sine, this part right here, and cotangent, just using the basic fundamental identities, plus the cotangent squared. Now we're kind of back to square one, but we remember that this doesn't have the nice antiderivative formula. So what we're going to do is we're going to replace that with the Pythagorean identity. And I'll remind you of that. These are very important. We know that the 1 plus the cotangent squared is cosecant squared. And I've written these with theta. Let me just go ahead and use the variables in the problem. I think that would be better. So here's our fundamental identity right here. So now we're going to do a replacement because we can anti-differentiate the cosecant squared in the 1. So this is going to give us a 2/3 cosecant x cotangent x. And now this will be replaced with cosecant squared minus 1, just transposing the 1. Okay, So now these are all antiderivatives that we know. This is the negative cosecant just from the last problem. This is the negative cotangent from the last problem, and that'll just give us a negative x. So these are all simple integrals. So now we'll just reel them off one by one. So this will be 2/3. So now we'll just say all basic integrals or antiderivatives. For Calculus 1 students, when you get the antiderivative, the indefinite integral, the definite integral, you've got all these terms, and some are synonymous and some aren't. So this will give us what? The negative cosecant, we just reviewed that, x, and then we have the negative cotangent, and then of course our friend here will just be negative x. And now we can tack on the c. And of course, if you want here, you can factor the negative, but this is fine. But just to make it look a little bit nicer, you can write this as negative 2/3 cosecant x plus cotangent x plus a c. Now, of course, this could be a Calculus 1 integral, but maybe not a very successful integral until students became a little bit more mature with their approach to calculus. But again, sometimes, like I said before, you don't even need new mathematics to do integrals like this. You just need some algebra using the concept of identity, an equation that is true for all values of the variables for which it is defined. And we use that all through here. So this is basically an exercise in trigonometry. And then, of course, the basic fundamental derivatives that we learn in Cal 1 allow us to do these integrals here. So I like how Webassine will say, do the integral, don't worry about bringing out the larger artillery unless you need it. So this is a good indication of how you can use what you already know to do an integral that is non-trivial, even though basic in format. Just takes more steps. And of course, you have the luxury here of just going ahead with the secant plus 1 conjugate method and not converting here. But I thought with this problem that it might be a little bit more straightforward this way, even though we end up with the type of a formula we have here, it might have been a little bit easier to get to that point. But that again is your choice. You always have a choice when you work a problem. There is no one set way to do it. So that's a good example. Now, I've got a few problems here from the section 1 that will cover some ideas we did at the beginning of the course. So let's look at some of these. Again, this will be maybe a little bit easier. I don't know, they're all about the same, I think. And then we'll look at that identity we used the first day to rewrite an expression that's rational in sine and cosine that doesn't require the major artillery I talked about before. So again, we've got an indefinite integral. So we have 1 divided by the principal square root of 1 minus 4x minus x squared. So again, the art of doing an antiderivative is understanding or discerning a pattern, and that's really the only way we can move forward. Unfortunately, the construct is much more difficult than the differentiation process. So we look at this and say that this is mimicking the inverse sine form. So the first thing we want to do is make an effort to complete the square. Now, you can complete the square in the integrand, or you can do a little sidebar. It really doesn't matter. Just for ease of use here, let's just go ahead and complete the square as a little sidebar. You can do it linearly with the integral, but sometimes it's better just to do the calculations as a sidebar. So first, let's notice we have negative x squared minus 4x plus 1. And just like you learned in pre-calculus, in order to complete the square, you need a monic polynomial. That is, the leading coefficient needs to be 1. So we're going to factor the negative from the first two terms, just like you did in pre-cal. Somehow students don't like completing the square, but it's okay. It never changes. So now, of course, we just take half of the coefficient of x and square it, which again is 2 squared. So we add and subtract, just like you've done in the first sections of our course. So now, of course, this is the perfect square. So let's just go ahead and write this out. I'll do some extra steps here just to make it clear. So this is the perfect square, which we write here. Let me not take the curly brace over too far. And then, of course, we have the minus minus. So this is a plus 4 plus a 1. So now we can write the perfect square. So if you like, let's transpose. This will just be 5 minus x plus 2 quantity squared. So again, you can do all of this under the radical sign in the integral, and that's fine. That's fine. That makes your work look very nice. But sometimes it's probably better to do the sidebar calculation to make sure that all the calculations have been done correctly. So again, just remember that we're trying to satisfy a pattern, and this gives us the pattern that we need. So now we can go back to the integral and fill this in. We have an identity. You certainly know what an identity is when you take pre-cal. By then, there's no excuse. You should know the definition. So now we've got the a squared minus the u squared, so to speak. So this is a nice 5.8 problem that you did. So now we can say that a will just be the square root of 5. Writing the 5 as a perfect square. So a is the square root of 5, and u is obviously x plus 2. So du is dx. So that's an easy antiderivative. So this has the sign form. So remember, just as a recollection, so to speak, du. There are always many ways to do things. A squared minus u squared, square root in the denominator, is the inverse sine form. So now we fill this in. So this will give us the inverse sine of x plus 2 divided by the square root of 5. So when we look at problems like this, there's not much to do except to put it in the correct form. And you learned how to do that very well in the earlier parts of the course. So I'm comfortable that you have good expertise there, but it's good to review this. And these types of integrals will come up as we continue our process learning new techniques. Now what I want to do is just a couple of examples that maybe give you the formula or the problem in a different format. A lot of you will go on to take differential equations. And so one thing that we like to do in mathematics is write things in differential form. So these are really some of the most straightforward differential equations that you already know how to solve. You don't have to take the course to learn this. You already know it. So here's an example that's written in differential form. So we have 4 plus tangent squared dy dx equals secant squared. And here we want to solve for y. the idea here is that we have a situation where we can actually separate the x's and the y's, so to speak. In differential equations, you call that separable. But what we want to be able to do is to isolate the derivative and then integrate with respect to x, which we can easily do here. So this is one of the preliminary type equations that you discuss in the differential equations course once you get some of the basic theoretical concepts out of the way. So what we want to do here is isolate the dy dx. So we'll just divide by 4 plus tangent squared. So we have dy dx equals secant squared divided by 4 plus tangent squared. So now, in order to actually determine the function y, we need to invert. That is, we need to apply the inverse process of the derivative, which is the antiderivative. So now we integrate. And a lot of, you can treat these as fractions and separate the variables, but I'll be formal right now. You can see why the notation of calculus survived, because there is no improving on it. This will never change. There is no more elegant notation that you'll see in all of academia. What you see in mathematics has changed everything in STEM. And we owe that to Leibniz, because he created this notation. So now this is just the differential. Dy dx is just dy. And now we can dress this up. Of course, this is the inverse tangent form. I'll go ahead and write this more formally. So now, of course, the integral of the dy is just the y. And then we'll tack on the arbitrary constant on one side. Now notice here, this is table ready. We have the a is 2. The u is tangent x. And of course, as we reviewed before, the derivative of tangent is the secant squared. So the differential is tailor-made there. So now we can easily anti-differentiate. This is table ready. And so we have the form. Again, you know this. A squared plus u squared, 1 over a, inverse tangent, u over a, plus a constant. So we can fill this in. So this will give us, in this case, 1 over 2, inverse tangent. And then we have u over a. So this will be tangent over 2. I'll just do the parentheses. So they don't absorb because of that 2 there. So don't make it up, plus a constant. So the interesting thing about a lot of these problems is that as you deconstruct them, so to speak, they're set up to provide forms that you understand. And of course, as you work more and more problems, the patterns are harder to recognize and you need more techniques. And so sometimes frustration can set in as you try to find a pattern that you actually understand. So this is what we call the separable differential form, the separable differential equation, because we can literally separate the variables and then actually solve for the unknown function by integration. And many times the equation that we derive is implicit. It's not explicit like this. So that's usually the implicit equation is the best we can do. And as you take your differential equations course, you will see that. I taught several honors differential equations courses before when we actually had an honors program. That's kind of died on the vine. But that is one of the most beautiful courses that you will do in your calculus sequence, because you get to use all of these nice techniques that you've learned, especially in Cal 1 and Cal 2. Now, there's a formula that we use the first day, and I want to say something about it that renders a particular integral very simple. And it's not to say that these sines and cosine rational expressions occur as integrands is something that you don't need to know is obviously false, because they turn up all over the place. And those of you that end up in maybe mechanical engineering or electrical engineering at the university will do some Fourier analysis, and you will be forced to reckon with those functions in other ways. So I want to remind you of this lemma that we thought about the first day. That is, we have a way of writing the sum of a sine and cosine with particular coefficients. So a sine x, we're taking a as a real number, plus b cosine x. You can look at this with a right triangle, but it has the formula. I teach with the Stewart Calculus, pre-calculus book when I teach pre-cal, and this is one of the exercises that you have in chapter 7. That's a really good book. So if you ever need to review some pre-cal, the Stewart pre-calculus text is a standard. Kind of like the Larson book we're using here in calculus. So this actually writes the sum as a single sine function where the tangent of phi is just b over a. So this is something we talked about the first day, and this allows us, for instance, if we had a configuration like this in a denominator, we could consolidate it, so to speak, and write one trig function in place of the sum. So this identity would allow us to write at least certain integrands in a simpler fashion without having to try some more complicated integration techniques. And so with that said, here's an example. Let me just go ahead and apply the one that we're going to use for this example. So this implies, so we'll take a and b equal to 1. So let's do a simple example here. We talked about this the first day. So in this case, a equals b equals 1. And so of course, here we get a squared plus b squared, which will be 2 square rooted. And then we have sine x, and then of course, tangent phi equals 1. So phi would be the inverse tangent of 1. And we know that's just pi over 4. So this is kind of the little calculation that we do. We may not always be able to get a nice formula for the phi, but in this case we do. So using our lemma here, we have a nice expression for this. So now if we see the integral like this, we have a way out. So maybe we are confronted with this integral. So with integration, you just assemble a bag of tricks, so to speak, a bag of techniques. So if we had this integral, you might look at this and say, okay, well, could I try the conjugate method here, do sine minus cosine, and then you get sine squared minus cosine squared, which is the negative of the double angle formula for cosine. And then you think, okay, well, that might be a way to do it, but I may not end up with some really simple integrals that I can do because the arguments are different. So that that might end up being a little bit more difficult than you want, but would be a possibility. But now, since we have this lemma here, we can simply make a substitution. So now we can replace sine plus cosine with this expression. Which is a lot simpler. Now, if you will, and this is where you need to think about what we do in this particular case. That is, we can simply rewrite the sine as the cosecant. So this will be 1 over square root 2, just factoring the constant here, and now writing this upstairs using the identity. So now when you think about this and you look at this, you're thinking, okay, here we go. We're back to Cal 1 and we haven't confronted this. We've done cosecant cotangent, we've done secant tangent, and those were simple antiderivatives, but this is a du over u. So let me give you a review here. This can be written a couple of ways. The cosecant x dx, this is the Lagrange method, the formula that he actually developed, is the natural log, the negative of the natural log of the cosecant of x plus cotangent. Now this is one form. You can actually use the properties of the natural log and bring this up, reciprocate this, and this is also equal to the following. So students always get bothered by this, so you got to pick one. They're equivalent, but they don't look the same. So if you do the properties, identities of the natural log, you can rewrite the argument here to get this. So it just really depends which one of these you want to use. They are equivalent, but they do not look alike, and then it's not always something that makes students comfortable. So again, this is a Calculus 1 technique. And again, for some reason, students don't seem to remember this. Maybe it's just too much at the end and you're just, overloaded. So now we can apply this. I'll just apply the first one. So we have the 1 over root 2 with the negative. And again, this is du over u. You should remind yourself how the algebraic trick to derive this. That's something you should be able to do. And so we'll get natural log. And if you will, just go ahead and put the arguments here. Cosecant x plus pi over 4 plus cotangent x plus pi over 4 plus a constant. Okay, so when we look at problems like this, we wouldn't look at this and say, oh, that's the antiderivative of this. This is where the difficulty in the anti-differentiation process ensues. You do not get things that, oh, that's clearly the antiderivative. So, and then you get to the point to where differentiating your answer to verify it is more cumbersome than just going back through the problem and checking your work. So when you're doing simpler antiderivatives, the differentiation check is fine, but when they get more and more complicated, that is not always the best approach. So again, notice here, we talked today about having these rational expressions of sine and cosine, and we talked about algebraic manipulations that can render the integrand into a simpler form. Well, previously we did the algebra. Here we use this identity that we have from pre-calculus. So again, whatever you can use, whenever you can use it, that's fine. We will take what we can get. So just remember that the process is noticing a pattern, and the pattern moves the problem forward. Okay, so this would be good. This is from your WebAssign. This would be good to know. Put this on a note card to review this. Review the derivation of these integrals. They're very straightforward. This is something you should have done in Calculus 1. So go back through that. Now, there's one other integral that I want to do. Again, this conjugate method we do quite a bit of. Just remember that anytime you have some basic algebraic identities, apply them to make the integrand simpler. That's the best way to move a problem forward without having to lose too much of your sanity. Now, as I look through these, there's not really anything here that's new based on what I have reviewed. But be sure when you work through these that you remind yourself of the techniques that you've done before. Write some formulas down, look at the things in a very analytic way so that you have good techniques to move the problem forward. Check your algebra just like you do with the application problems. The WebAssign, again, is a wonderful tool. As I've said many times, it's smarter than we are. It's been perfected, and it offers a wonderful tool for learning math, but it can be somewhat frustrating, but it will make you better. And again, I remind you of the 10 years of students that are now engineers or PhD candidates or master's recipients that I have taught using WebAssign in this book. Again, excellence in STEM is consistency in utilizing textbooks that are state of the art in the sense that they give you the instruction that you need to move your knowledge forward. Free resources are good, but they are filled with errors. And so we want to make sure that the education that you get is good and something that you can depend on. Now, when it comes to the next type of integration process, I will say this: you already know it. You just didn't know that you knew it. So it's called integration by parts. So it sounds really, difficult in the sense that, well, we haven't really called anything that, but you have learned the product rule, and that's the basic idea of integration by parts. Integration by parts. So, like I said before, this is probably the most important technique that we will learn. And then, of course, we'll add to it some other ideas. But this is basically the way that you can construct many integral formulas for integral tables. So let's recall the product rule in differential form. Now, I'm going to give you some techniques to make this clear and make this technique very straightforward and efficient. I've worked on these for several years, and the problem is students have trouble keeping up with signs, pluses and minuses, and they have trouble organizing. So I'm going to try to give you some organizational methods. So remember, if we have, let's just say U and V are differentiable functions. Say differentiable functions of some variable, say of X, if you like. And so if we do the differential of the product, that will be U dV plus V du. That is, when you take the differential of a product, you differentiate one factor, leave the other one alone, and then vice versa. So the product rule was the result of work with Leibniz, and we still use his notation. So what we want to do in this particular case is to integrate. That is, integrate. So when we integrate, and we've got an integral in our formula, so we're not going to put a constant anywhere. It's going to be buried in the integral that's part of the formula. So we'll use the linearity here of the antiderivative. And then, of course, here, the integral will undo the differential. So these are all equivalent. And now what's preferable here is to actually isolate the UDV. That's the standard technique here. So we want to isolate that. So this will give us the integral of UDV equals UV minus the integral V du. Now, this is what I'm talking about when we discuss integration by parts, the parts being, in this case, the U and the dV. So you're actually assigning particular parts of the integral to be U and dV, and then computing the right-hand side here. And you might say, well, what's so great about this? Well, the idea here is that by integrating by parts, so to speak, you actually produce computations over here that you can do. So this integral here may look very difficult, and you'll get better and better at this. You'll look at an integrand and say, oh, I can use parts on that. Oh, that'll work with parts. And so the basic construct here is to be able to, from U, get the du. So that means you need to differentiate. And from the dv, get the v. And that means you need to anti-differentiate. So if we were going to draw this like in a table very formally, we might have something like this. We'd have a u, and then we'd have a dv here. So I think of this as a differentiation column and an integration column. It's funny, when I was in grad school, I mentioned this to one of my professors in probability. He says, well, I don't do that. And I said, well, it'll help you from making a lot of mistakes. But again, it just depends what you learn. This is kind of like the Oliver Heaviside techniques. Oliver Heaviside was a British mathematician and engineer, and his techniques have survived. So the idea is if we differentiate this differential style, we get du. And if we integrate the dv, we just get the v. And of course, we have constants running around, which we'll just absorb into this for now. So when you do this, this would be a way of organizing the technique and saying, okay, we need u times v. So we do an arrow here and just put a plus there. Just kind of like reminding us that there are no negatives here. There might be negatives buried in u and v, but there's no negative in the formula. And then to get the v du integral, we have the horizontal line here with the minus sign. So for instance, if I drew this diagram here, then I would pick a u and I pick a dv, and then of course you don't always have to be so particular about the adding the dv's and the dus. I'll show you that. And then do this diagonal uv, that's this term, and then do the horizontal line v du. The horizontal lines would take the integral sign, the diagonal lines just as product. So this would be a way, this little diagram here would be a way of organizing this formula. So again, you can be extremely formal here. Basically, all you have to do to get this process to work is you have to differentiate u and you have to integrate the dv. So whatever you have here, you better know how to differentiate it. And whatever you have here, you need to be able to integrate it. So that's the key. Together, it makes no sense. But when you break it up into parts, these parts are easy. That is, you can do this integral, you can do this derivative, then you put it together with this formula. And then, of course, you keep your fingers crossed that you can actually do this. So this is how students figure out if they made good choices for U and DV. They can actually do this integral. So let's look at a simple example. This is right from your WebAssign. Say we have, and this when I say one pass, this is one pass of integration by parts. I'll show you how to do more than one pass in a simple way to execute the integration by parts when you have a very simple setup. So again, the simplicity is what we have to look for. So say we have x squared natural log x dx, and this is an indefinite integral. Now, when you look at this, you're thinking, okay, ln x, I understand when I differentiate it. I mean, I'm okay with that. And x squared, I can integrate that. That's just the power rule. So in some cases, you're going to say that's integration by parts, because if I break it up into parts, then I can do it. Now, I'm going to be very formal this time. Then we're going to relax the notation. But let's go ahead and think of the parts here. So we do your D for differentiate and do the I for integrate. This is Professor Ron's notation here. Dr. Larson alludes to this somewhat in the text, but this is what I do, and it really is good, especially when you get the Laplace transform in differential equations and you're trying to keep up with all these parts formulas. So what we're going to do is say, we're going to choose the U, and you can say U equal, but I'm just going to stick U right here. So remember, there's the U, so this is ln of x. Okay, so that's the U. You can say U equal. We don't need to. You know that's U. Just follow the diagram. And then the dV is going to be ln x dx. Oh, excuse me. X squared dx, the easy part. We don't want to choose the same, obviously. So x squared dx. And then some students say, well, Professor Ron, do we have to put the dx there? I can just add one and divide by the new power. Sometimes we get lazy and leave it out. But now we see that the U is the ln of x, and the dv is the x squared dx. Now to go to the next row, we want to take the differential. So this will be 1 over x dx. Okay, so we're putting in all the differentials here. We can get lazy if you want, or you can put it in, that's fine, no problem. It's not going to make any difference. You're going to stick the dx in there when you write this anyway. So again, something we can do, we know the derivative of ln of x, it's 1 over x. And now here we're going to add 1, divide by the new power. And don't put any constants in this. We'll stick a constant in at the end. So don't worry about putting any arbitrary constants in this integration here. We'll take care of that at the end process when we actually say plus a c. So this will be x cubed over 3. Okay? This is so simple, it may seem difficult. It's so simple. The beauty of this process is that I could have taught you this in Cal 1. Well, none of you took me for Cal 1, unfortunately. But the idea is, this is something you can teach Cal 1 students, but you have to teach so much in Cal 1, there's no time for it. So we reserve this for Calculus 2. So now what we do is we do the arrows here just to organize the work. So we have the plus and we have the minus. This technique just organizes your work. A lot of you would use this for the product rule. And so now we can fill it in. So ln of x times x cubed over 3. So we'll just do that first. We'll do 1/3 x cubed ln x. That's the UV. Sorry, I get all over myself. The sad part about these nice pens here is that they drip, but they make great, they do really good, forms here on the paper that you can see. Now we have minus, notice minus, in this case, b du. So let's write it in. X cubed over 3 times 1 over x dx. Okay? Now that's done. That part's done. The UV's done. Then, and we can do this. So let's simplify. So we have 1/3 x cubed ln x, and now we've got a 1/3 here. We can factor that, and then of course the x absorbs into the x cubed to give us an x squared. So now what we see with this very simple example here, and I think sometimes, like I said before, it's so simple that it's like, I'm just making this up. And now you're thinking, okay, add 1 divided by the new power, just like we did there, we're done. So we get 1/3 x cubed ln x minus 1/3, then x cubed divided by 3. And now we can add the arbitrary constant. So don't worry about it here. Just add the constant as a final measure, and then we can reduce this a little bit. You can always factor these, but for now, just leave it as it is. And then we get minus 1/9 x cubed plus c. Now, of course, if you look at this, and like I was saying before, I'll say leave it as it is. We could get a common denominator of 9 and factor this and make it look pretty. So let's just go one more step. We'll do the 9. We don't always do this, but it's good practice to do it. And then, of course, we can factor the 1/9, and we can factor the x cubed. So that leaves a 3 ln x minus 1. Now, of course, if you do this, that doesn't make it any more correct. You could clearly stop right here or right here. But sometimes it's just, you know, practice your algebra, make your formulas look nice and neat, but that's certainly not required, and WebAssign's not going to be upset if you don't do it. Okay, so what I want to show you here is that the integration by parts, ladies and gentlemen, you already knew how to do. No one ever showed you this. So basically what we see here is we don't have to learn any new mathematics. We have the product rule, which can be recast into this formula. And so every time you do your integration by parts, you have to assign a u and a dv. And then you simply differentiate, integrate uv minus integral v du. So with this little tabulation here, you can organize your work. Keep track of signs, check your work. It's easier. If you can kind of do this as a table, then it's easy to fill in this formula. So when Dr. Larson writes this in the book, he'll say u equals L, and we'll do u and dv and all that. What I decided to do was to write it this way and basically put the ideas here that are most important. Now, of course, when we apply the process more than once, we won't be as formal with the differentials and all. We'll just know that they're there when we write the integral, because it really won't make that much difference. If I left the dx out of here, you just say x cubed over 3 times 1 over x and tack on the dx, because you know it lives there. So that would not be a problem if we relax this a little bit. Okay, so just keep that in mind. Note that this and this are doing the same thing. This is organizing this formula here in a way that's easy to work with. All right, so I will give you little tips like this as we do these problems. And of course, as your own mathematician, STEM professional, you can make techniques that work best for you. I just think that students find this to be very straightforward. Now, let's look at an example where we have a very common situation that occurs in integration by parts. And students want to be, let's just face it, say we're doing an engineering problem or we're doing a problem in differential equations and we've got to do integration by parts, and maybe we use an integral table or maybe we don't, but we want to be efficient. So for instance, say we have the following integral, and this will be a very easy integral. Look at this integral. We have the integral of x times e to the 3x dx. Now, when you look at this, you think of two things here, and this is what's important. We have e to the 3x, which is an easy antiderivative. So I'm just going to make a couple of notes here. We'll say we know this, e to the kx dx, where k is a constant. We'll just say k element of r as a constant. We know this is 1 over k e to the kx plus a constant. That's an easy antiderivative. So we're going to say our easy integral. I want you to make that observation. Now you're thinking, if we chose this for the dv, this part here, x, taking the derivative of x is very simple. And we're going to note that x is a polynomial that differentiates to 0. So I'm going to do this problem two ways, but I'm trying to note here for you that we have a very common situation. That is, we have a polynomial x that if you keep differentiating it, you eventually get 0. You differentiate x twice, you get 0. You can integrate e to the 3x all day long. You can do that in your head. You just get 1/3 e to the 3x. Then you do it again, you get 1/9 e to the 3x. It's not very difficult. So you're thinking, there might be a way I could do this integral quicker. So I'm going to do it two ways. First, we're just going to look at it the way we did the last time. So we're going to have d and I. So we're going to take x. So anytime we have a simple polynomial or just a polynomial, we're going to always choose that to be the u. And then the easy integral is just that. We're going to put this here. So you're thinking, okay, well, this was easier than the last one. So we get 1 dx. So I'll be formal, even though I just really want to put 1, because who needs the dx? We know it's there when we anti-differentiate. And then here, applying our simple integral formula, 1/3 e to the 3x, right there. So you're thinking, okay, so ub minus the integral v du, right there. Okay? So you're thinking, all right, well, Professor Ryan, that's easy. I can do that. I'm just going to go ahead and fill it in. So we have uv 1/3. We'll take the 1/3 out, and then we'll have the x e to the 3x. You can put it in any order you like. It's like that. And then the v du comes across this way. The horizontal lines are the integral lines, and that'll be the negative. So minus the integral 1/3 e to the 3x dx. Right there. But of course, that's an easy integral. That's just like this one. So let's finish it. So we get 1/3 x e to the 3x minus, go ahead and factor the 1/3. And now we can just apply the simple integral formula again to get another copy of 1/3. So this will be 1/3 e to the 3x. Now we have 1/3, 1/3 minus 1/9 e, and sorry, I left out my x. Need that x. 1/9 e to the 3x plus a constant. Now, when you look at this, and of course we could factor this, we can get a common denominator and factor it and make it look nice and all that. And you're thinking, Professor Ron, that was easy. I mean, why would I need anything else with this? Here's something that Oliver Heaviside developed, the British engineer and mathematician that I talked to you about. The tabular method here is basically what we're doing for any integration by parts problem. But one thing is that you can actually do 2 passes of integration by parts with this form and be done with the problem. Let me show you that. Let me just show you the second approach, which we're going to use, so you're going to have to learn it anyway. So I'm just going to give you the second approach. I just want to make sure that you understand that we will arrive at the same response, the same antiderivative. So the second approach is just to apply a second pass of integration by parts, basically to do this integral here without having to do it. So here's what I'm talking about. So here we can start the same way, x, and now I'm not going to put in all these dx's. I'm going to leave them out. This is where we relax the notation. So we have x e to the 3x. So we're going to relax the notation. That is, I want to differentiate this and I want to integrate this. But notice here, I'm going to differentiate the x to 0. So I'm going to do 1 and then 0. Now here, I've got the same thing, 1/3 e to the 3x. Now, here's the thing. This would be a new integration by parts right here. So I'm going to start over again. That is, now I've generated a new integral, and now I'm going to apply integration by parts. Here's the first pass. Here will be the second pass. Well, the second pass, if I differentiate again, I get 0. And if I integrate again, I get 1/3 times 1/3. So this will be 1/3 times 1/3 e to the 3x, which is 1/9 e to the 3x. Now, here's the thing. This is the first pass, and this is the second pass. So first pass, that's what we do it. And then we apply it again, new u and new dv, second pass. But because of this minus sign, after here, there's going to be no more content. So what we can do is do the plus, and then because of the negative sign in the integration by parts formula, do the negative. So when you draw diagonal lines in the integration by parts form, you alternate plus minus, plus minus, plus minus. So now we've done the integral in the second pass without doing it. We did it by integration by parts using this table here to do all the work for us. So now what does this imply? Well, we're done. This implies that the integral x e to the 3x dx, we just connect the diagonal lines. This will be 1/3 x e to the 3x, and then minus 1 times this, minus 1/9 e to the 3x plus a constant. Same response. Much easier. But with that said, it wouldn't matter if you did it that way, because this problem is so easy, even done with this technique is still simple. It's just that if you want to apply the integration by parts a second time, then you don't have this, big show about, well, here's the new U and here's the new DV. You just select it right here and then do the process again. It's kind of like doing synthetic division. You bring the coefficient down, multiply, add to the second coefficient. Then you do it again. You keep going. That's the same thing we're doing here. Here's the first pass, here's the second pass. But now that this zeroes out, the diagonal lines will just give us a bunch of zeros. So this form here organizes the parts computation for this scenario. That is, this will not always work. So don't even think to apply this unless you have this scenario. That's where it takes a math student who understands what they're doing, in the sense that you don't just make blind techniques. You do what you do because it's based in understanding. So if we have a polynomial like we have here, x, because we know it differentiates to 0, and we have an easy integral that we can do over and over and over with little or no work, this method is the way to go. This is the Oliver Heaviside method that makes the process of reapplication of the parts formula very straightforward, without having to reassign like we do here again. This is what I find to be extremely useful when you have forms that either repeat or forms like this where you have the polynomial differentiating to 0. So you have the choice. When you have this, you can do the second application. It may be that this integral that you get here really does require another application of integration by parts. Okay, and if that's the case, you have to do it again. So what I'm saying is that we may not even have this situation, but we may need 2 passes of the integration by parts in order to finish the integral. And so we'll find that this will be useful in other situations. So what I want you to do with this is notice that when we do the first and second pass, we relieve ourselves of the differentials. We just move them out of the way because they get in the way. And then we let the problem solve itself. So this is a notational convenience here that we didn't have here because we're doing everything formally. But it's the same process. And it is based in the theorem of integration by parts. And it's kind of like when you're doing factoring, Professor Ron's AC lemma, it's an efficient approach to keeping track of signs and keeping track of the actual terms in the integration by parts formula. Okay, so now let's try another one. Now, this is the first idea of this, and so we'll do another one. So if we come up against this again, we'll try it again. So I want to give you techniques that you can use. Now, this next one actually turns out to be just a 1 pass, and then we'll do one that requires 2 passes again that has the same scenario, but I want you to get well steeped in this. So example, business calculus students usually end up getting problems like this one. We have xe to the 4x, and we have 4x plus 1 quantity squared dx. Now, when we look at this, we're thinking, okay, well, Professor Ron, we don't have anything simple, like we don't really have a polynomial that differentiates to 0, because we certainly wouldn't want to try to integrate the e to the 4x over the 4x plus 1 squared. That would be difficult. But the 4x plus 1 squared downstairs would make it easy, add 1, divide by the new power. So we're thinking, that's not half bad. And then, of course, the x4 to the ex, we can differentiate that, by, no pun intended, by the product rule. So there is hope for this problem with integration by parts. So what I'm going to do first is I'm going to write it in a suggestive form. I'm going to write this x e to the 4x times 4x plus 1 to the negative 2, kind of like we did in the last set of exercises. If you don't take the time to study this with purpose, And with utilization of good algebra, you will come to grief. So again, I want you to be sure that when you set this process in motion, you are comfortable. So now we're thinking, okay, well, how else are we going to do this unless we use integration by parts? So this is what we're going to use for the U, and this is what we're going to use for the dV, because again, that's an easy add 1 divide by the new power, and you just got the 1/4 from the chain rule. So that's an easy integral. So let's do it. So we're going to have differentiation, and we're going to have integration. But of course, the differentiation is going to take a little bit more work. So we'll leave some space for it. X e to the 4x. And you'll see how this works out nicely algebraically. And then we have 4x plus 1 to the -2. And if you want to go ahead and put the dx in, that's fine, because this is the formal approach. This is not two passes. So now, first we're going to kind of do like a extra line here, and then we're going to move everything down 1. So I'm going to move this all the way down here, but just a little side calculation here. By the product rule, this will be e to the 4x plus 4x e to the 4x, just by the product rule. Differentiate the x, then the e to the 4x. Well, that's so simple. E to the 4x is our friend. And of course, this is the dx. We're doing this formally. So now we'll factor the e to the 4x, e to the 4x, and this gives us the 4x plus 1, which is kind of convenient for this problem. Okay, so I did a little side row there, extra space. So I'm going to bring this down to here so that the rows actually match up. So now here, I've got the 1/4 that I need from the chain rule. Then I add 1 divided by the new power. Well, the new power is -1. And if we divide by -1, that's just a negative. So we get -1/4. And now I'll just go ahead and write it downstairs so it's easy to see. 4x plus 1 to the 1 power. And you can leave off the constant. So now you're thinking, oh, well, how convenient, the 4x plus 1s will absorb, and I'm left with an integral that we can all do. So here's a situation where the integration by parts was really good, but it appears that we only needed 1 pass. So now when we connect UV integral B du. So we take this and say, what's this equal? Okay, well, the UV, so we get a -1/4. We'll pull that out to the side, -1/4 x e to the 4x, and then times, and we'll make a fraction out of that, 1/4x plus 1. So again, -1/4 x e to the 4x, and then the 1/4x plus 1 right there. That's the UV right there. UV. Minus, again, the minus sign comes here. And of course, now notice we have the minus with the minus. This is where this table is very useful. We have the minus with the minus. So that becomes the plus. That's why this particular setup is very efficient. We have the minus built in from the formula, but then we have another minus here. So we multiply, we get the plus. So minus minus is plus, and we get the integral 1/4. And now notice we have e to the 4x plus 1. And then we have the 1/4x plus 1. So I'm writing out all the steps so we're not leaving anything behind. So again, minus minus gives us the plus. We have the 1/4. We have the e to the 4x times 4x plus 1 times 1/4x plus 1. And so now we can clean this up a little bit. This will be a minus x e to the 4x. And then we can bring the 4 downstairs with the 4x plus 1. And now, of course, here, all of this, gives us a nice integrand. A lot of things absorb. first, well, let me leave a little space for the 1/4. No reason to cram it into the integrand anymore. Let's go ahead and factor it. So now the 4x plus 1s, they absorb, and so we get e to the 4x dx. So what we've resulted here is a very simple integral. Again, a very simple integral to do. So this will give us negative x e to the 4x divided by 4 times 4x plus 1. And now, of course, we get the 2 1/4. So the 1/4 from this integral. So this is 1/4 times 1/4, which is 1/16. I feel like I can combine that step, ladies and gentlemen. I feel like you're okay with that. And this will just be e to the 4x. And then we have plus the obligatory constant. Now, what we can do here, now this is the antiderivative here. And again, if you wanted to try to make this look a little bit nicer, we can get a common denominator here of 16 times 4x plus 1. So let's just do that and see what happens. Four x plus 1. Don't have to do it, but just a little bit of algebra practice. So again, we need the 4 here. We got the 4x plus 1, so that'll be minus 4x e to the 4x. And then here, we just have plus. So we got the 16, but not the 4x plus 1. So we have e to the 4x times 4x plus 1. Just getting a common denominator. But now, of course, the 4x times e to the 4x and the negative 4x times e to the 4x, they absorb. So we can say absorb. So that leaves us with e to the 4x in the numerator. Again, this is optional, but sometimes you can see some simplifications that you know, are kind of nice. So that would be the antiderivative. Again, you can certainly stop right here. There's nothing wrong with that. That would be fine. But if you do the algebra, then it's easier, less to actually enter. So what I wanted to notate here is that in this particular problem, nothing unusual going on. We didn't do 2 passes of integration by parts. We simply just did the regular standard approach. That is, we thought, okay, how are we going to do this? The only recourse would be to say, I can differentiate this, so that's my u, and I can integrate that, so that's my dv. So again, this problem was tailor-made for integration by parts. Now, when you think about this, these formulas are not intuitive at all. When you look at this, just like, I don't know, I don't see this. It's not like you can look at this and say, oh, for sure, that's the antiderivative. It's not, you can look at it and say, well, that maybe is an antiderivative. But this particular process here, you can see how valuable the integration by parts is. What it basically does is it breaks down an integrand into 2 pieces that you deal with separately, and then you combine them. And the combination results in a simpler integral. For instance, if you make a substitution and this integral here is harder than the beginning one, then you got to go back and make another substitution. And that's okay. It's like when you started the anti-differentiation process in Cal 1, you had some misfires when you do that. Okay, now, excellent. This is a nice problem. Again, you should be happy that I work on your WebAssign problems. Ladies and gentlemen, the key here is to give you techniques. I don't want you to start your WebAssign like you've just been pushed out into the deep end. But you work these problems, you rework them, and then when you're tired of them, you work them some more. That is how you achieve excellence in mathematics, okay? So I can say that to a Cal 2 class because this is imperative. STEM professionals must understand calculus, especially the computer science ones, the math ones, the physics ones, and the engineering ones. And these days, everybody wants to be an engineer. So welcome to math. Okay. Now, what I want to do is another example of two passes. And then we'll try three passes. But it'll be so easy, you'll be like, why don't we start this one first? So what I want to do is give you an integral that you actually did in Cal 1 by miscellaneous substitution. And this is so easy with integration by parts. So when you learn Cal 1, you learn miscellaneous substitution, and you do quite well with it. It's a very important technique. It just simply transforms the integral into a rational function. And then you add 1 divided by the new power, which is, or get some integral formulas that you know. So in your previous life, this would be, the u would be here, and you'd square everything out, and then you create a nice rational function or polynomial, and you'd be good to go. Now we can look at this differently. We can look at this as an integration by parts formula. So I'll just say before we had miscellaneous. And different techniques, remember the antiderivatives may look different, but they differ by a constant. Before, and so now integration by parts. So when we look at this, we're thinking, oh, I see what you're saying, Professor Ron. This is like the last problem. That's an easy antiderivative. We just have x minus 6. So we don't even have the chain rule just gives us a 1. So we just have add 1 divided by the new power. And of course, that's a polynomial which differentiates to 0. Wow. So write this down. X corresponds to polynomial, and we'll say differentiates to 0. Do me a favor. If you use this, you make sure you have this situation. Do not send me a message in WebAssign where you have applied this incorrectly. That will make Professor Ron upset because that means you're not listening to me. This is a very special situation where we can do this differentiation to 0. That is, we have a polynomial and we have a very simple antiderivative. So you make sure if you apply this that it actually does work. And then just say this, x minus 6 to the 1/2 is an easy integral. We can do more than one pass, and we don't have a polynomial, and we'll do some of those. But this is the easiest scenario to start with, beyond just the basic one pass, which we have done. So now you're thinking, okay, well, we're not going to do this two ways this time. We're just going to utilize this scenario here, and we'll be relaxed in our notation. So now we have the x. We're just going to say x, 1, 0. Again, this is going to be two passes. This will be the first pass, and we don't formally have to assign a new u and dv. It's right here. We don't have to do it again. Second pass, it's done for us. This is an ingenious technique, and I actually was exposed to this as an undergraduate at Carolina. I had an old calculus book that was written in the 50s, and Oliver Heaviside was all over that calculus book. So yes, it's a technique that's been around a long time. So now we have x minus 6 to the 1/2. Now again, we're relaxing. We're not putting in the dx's. We're just getting the antiderivative in a relaxed mode. So now add 1 divided by the new power. Again, the chain rule just gives us a 1, so we don't have any fancy coefficients. So the new power is what? 3/2. And we flip that and we get a 2/3. How simple is that? How simple is that? So simple. Okay, well, again, we're going to need to do this diagonal and this diagonal for the second pass. That'll be a 0 contribution, so we're done. So we need to integrate one more time. Okay, so now what we do is we add 1 divided by the new power. So we have the 2/3 out here. And then when we add 1 to 3/2, we get 5/2. Reciprocate 5/2 gives us 2/5. So nice how this works. X minus 6 to the 5/2. Right there. That's it. And we can multiply that and get 4 over 15, but that's fine. We can do that. So now look. Plus, there's our first UV, and this is the second UV with the second assignment, with a minus sign, because of the minus sign in the integration by parts formula. It's amazing. Miscellaneous substitution is time consuming. This is easy. And you're thinking, wow. I had a student one time, like about 6 years ago, who was taking Cal 1 and it had AP calculus in high school, and he already knew how to do integration by parts. So when he'd do his problems, he'd use integration by parts. I was like, well, good for you. But he didn't know this method. I shared it with him. And he thought, oh man, that's really easy. But you know, I know all of you have had some form of calculus somewhere before, Sam Jack. Most of you haven't. If you haven't, it doesn't matter, because I teach you the methods that you need to know. But now we see connection, connection. So now the integral 2/3 x, and then we're going to make it look pretty because we want to work for the FBI maybe. So we have 2/3 x times x minus 6 to the 3/2 plus right there. Now here, notice we have the minus that's built in, but no other minuses. So this gives us minus. So we have 4 times divided by 15, 4 over 15. And then we have x minus 6 to the 5/2 plus a constant. Now, when you look at this and you think about this, this is like a problem in pre-cal where they say factor to death. Because maybe you were doing a problem and you needed to analyze zeros and you're thinking, I don't know what they are. So if you're doing your WebAssign, ladies and gentlemen, this is sufficient. This would be a correct answer, and WebAssign would give you a thumbs up, would give you that green check that you all look for. But let me just show you the technique to make this look a little bit simpler, because it's good practice. So first, let's just go ahead and get a common denominator of 15. So 15, that'll be a 5. 5 times a 2, that's a 10. So we get an x. And then we get a 4 over 15. X minus 6 to the 5/2, just to make it look a little bit more presentable. I remember when I was a kid, looking in the calculus books and all, that formulas would always be so refined, and we'd spend more time making our formulas look like that than we did doing the problem. So it's good to practice this. Now we can see, we can extract the, we've got a 2 in everything. We can extract a 2 over 15 and then a 3/2 copy of x minus 6. So we've got the 15. And again, this is 2 times a 5. This is what I do for my pre-cal students, and somehow they still manage to forget. And then we can extract the 2. And then we have the x minus 6 to the 3/2. So now when we look here, we extracted the 2 and the 2, but we left behind the 5 and the x. Okay? And now here, we left behind the 2, and then we have 2/2 copies of x minus 6. So we have minus 2 x minus 6 to the 1, because the 3/2 from the 5/2 is 2/2, which is 1. So I'm doing this because you may not have done this recently and you need to see it. So now we have 2/15, and of course this would have been done in Cal 1 anyway. And if not, you're seeing it now like you should have seen it then. So now we have what? We have 5x minus 2x, and a negative negative plus a 12 plus a c. So now we've got a nice little factor here that would allow us to analyze this particular function, which is useful to us. So we have 2/15, and we have x minus 6 to the 3/2. And then, of course, now we have a 3x plus a 12 plus a constant. Now, like I said before, don't put any constants in this work. Put the constant at the end. We will do some definite integrals with this, but we have to get good at this. If we have a definite integral, in this case, we have to slap it on this and this, or we can reduce it down to this and put the limits of integration here. It's okay. It doesn't matter when you do it. Usually, these two terms may be significantly different, and we just apply the upper and lower limits separately. So that'll be something that we'll do. But again, we need to get good at this first. So let me just remind you here, we have a miscellaneous substitution problem from Cal 1 that we can now do using integration by parts. And then noticing the fact that we have a polynomial, again, that differentiates to 0, just observing that. That's not trying to be redundant, just observing that. And then we have a component here that has an easy integral. So it makes it very easy to apply 2 passes of the integration by parts, where the second pass is done for us automatically. Here's the new u and the new ud, boom, we do it one more time. So this form here organizes the process in a way and keeps track of the pluses and minuses. And we will also do it when we repeat the integral. So we're going to do, of course, the minus here horizontal, and then the second horizontal will be plus. So the horizontal lines will also alternate in sign, starting with minus, plus, if we ever need to do that. So this technique here that was initially developed by Heaviside is a remarkable one, and is truly efficient, and is very great for helping us to keep track of signs. That's the issue with this. Students are always confounded by the signs, and this takes care of that for you, okay? So again, it does take some time to get used to integration by parts, but it will be well worth your time. Now, I want to do an example where we actually have a fairly straightforward integration by parts, but I want to do an integral that repeats. Let's see here. I'm going to go ahead and do this one. I want to do an integral that repeats, and then we'll do more of these next Monday. This integral comes up a lot in Cal 2, and I want to show you how we can do the repetition process. So this just requires one pass. You can do integration by parts problems all day long. I mean, they're wonderful problems. So here's an integral that we encounter quite a bit. And I want you to practice on this. Okay, get some good practice with this. Get a head start. That's why I'm going ahead and going over this. Get a head start on this. Now, with this particular problem, we're thinking, oh, secant cubed, that, no fun. So we're thinking powers of trig functions would actually be good for integration by parts, because you can break up the integrand and produce what they call reduction formulas. So here's a good place to start thinking about that. So we're going to think about breaking up this integral into 2 pieces. And here's what we're going to do. We're going to just use the power rule. So this is not a trivial exercise. I remember in grad school, I had to remind some of my friends in the engineering department about this technique. They were taking an applications course, and I was just hanging out in the class. And they said, Ron, how do you do this? I said, well, my calculus students can do this. So now, when we look at this, we think about the easy integrals that we have. We know we can easily integrate secant squared to get tangent. Okay, that's an easy integral. And we know the integral, or the derivative of secant, is secant tangent. So we're thinking, let's try parts with this. So, and what's going to be interesting about this is this integral is going to repeat in the parts process. So we're going to use parts. So we're going to start with u equal secant x. And we're going to start with, and we'll do this formally, even though I don't like to. I mean, I think you know that what we have here. So this is the formal process where I put the dx's. If you want to leave it out, feel free. It's not really going to confuse you. If it does, then you've missed the whole point of this exercise. Now, when we look at this, we're thinking, okay, well, the derivative of secant is secant tangent. So we're thinking, if we don't do parts with this, how are we going to do it? You know, just, I don't know. So now, again, our simple integral from Cal 1, the antiderivative of secant squared is tangent. So that's one pass. So we're going to say uv minus the integral d du. Now, what's interesting about this is that doesn't look too promising, but this is why I did the Pythagorean identities before, and just every problem had a Pythagorean identity in it. So this says, what does this equal? Well, this equals this, so now we apply parts. So we have uv, so we have secant x, tangent x. And then minus the integral, oh, and of course, be formal here, put the dx there. Let me give it a little more space. Since I'm being formal here, I don't need to do it two different ways. Okay? So now we have minus the integral. So we're going to have a tangent times a tangent and the secant. So we have secant x tangent squared. So integration by parts says uv minus b du, right there. And you're thinking, how can we survive with this one? We're going to use the same identity we had before. Remember, tangent squared is secant squared x minus 1. That's the Pythagorean identity. So we're going to use that. Symbolic computation is what I do. When I do arithmetic, it's symbolic computation. You will get better at that. And all of you are good, but you're going to get better at it because I'm going to keep doing it the whole class. Okay, so now we're thinking, oh, good, there's a secant cubed, which is going to replicate that. So we're going to have the integral repeating itself. It's like an algebraic problem where you have an x and a negative 2x, and you put all the x's together. So this is something you've done before, but you've just never done it with integrals. So this equals secant x tangent x. Now we'll go ahead and multiply this out. Secant cubed. And then we have a minus secant. So now we'll expand that. So this equals, and then I'll write it again at the end. So we have minus the integral of secant cubed, and minus plus the integral of secant, which we know. So now we have the integral of secant cubed equals secant x tangent x minus the integral of secant cubed plus the integral of secant. So I'm going to add secant cubed integral to this one. So equivalently, 2 times the integral of secant cubed. I'm not skipping any steps here. My students probably think, you all think I'm probably crazy, but I'm putting in all the steps. So this will be secant x tangent x plus the integral secant x dx. Now we know this, that's the natural log from the Lagrange procedure, and we can divide by 2. So first we'll say this is 2 secant cubed x dx equals, go ahead and do that integral, secant x tangent x plus natural log absolute value of secant x plus tangent x. That's the other integral form that we use from Cal 1. Now, I'm not going to tack on the constant yet. I'm just going to hold off to the end because well, if you want, you can just call it a C1, then we'll divide C1 by 2 and call it C. That's okay. Put it wherever, or just stick it on at the end. It doesn't matter. So now we have secant cubed integral will now be 1/2 times all of this. So this is a very important integral that we're going to remember or try to remember. And now I'm just going to reassign that to be C. So here's a very important integral formula that often is found in your integral tables, or it's found in a reduction formula. Of course, you can write this with U's. Let's see. So now, this is where I wanted to give you the first example of the repeating of the integral. So when you look at a problem like this, you're thinking, okay, this is truly algebraic. We're getting an algebraic equation from the integration by parts technique. So we only have one pass. And I did all these steps out in complete detail so you can see this. We start with an integrand that doesn't really give us much place to go algebraically, depending on, based upon what we already know from Cal 1 and the Cal 2. And so when we look at this particular setup here, we think, okay, well, secant cubed can be written this way. And why is this an improvement? Well, this is an algebraic manifestation that says, okay, let's consider integration by parts. And we make the assignments in this case based upon the fact that this is something we can differentiate, and this is a function that we can anti-differentiate. So at first you're thinking, okay, is this really what we need? Well, we apply one pass of integration by parts, and the key is just recognizing that we utilize the Pythagorean identity here. And so upon doing that, and I've done all the steps maybe in maybe too much detail, but what we see here is we get a copy of this integral on the left-hand side on the right-hand side. So now this becomes an algebraic equation to find a formula for this. So just like having, you know, an x, for instance, we have a x and a negative x. You put all the x's on one side to get 2x. That's exactly what we're doing here. Just remember, if you don't like dragging this around, you could call it an uppercase A if you wanted, if you just wanted to make a quicker notation for it. But it's just an object like any of these others. And so once you have that, the integration by parts formula has basically resulted in integrals that we know. This we get for free, that's just UV, but that's an integral we know from Cal 1, just like the integral of cosecant. And so then once we fill in all the easy details from Calculus 1, then we can simply algebraically solve for the integral upon division by 2. So the reason I'm doing this integral is, unfortunately, this occurs a lot. This comes up all the time, and then you're like, we're not going to redo this integral every time we see it. That's ridiculous. So we're going to have this in our back pocket when we need it. So go ahead and put this on a formula card and say commit to memory, or at least put it somewhere where you can access it and use it. Because when we see integrals like this, we're thinking, well, we can use a reduction formula because we forgot it. That wouldn't be a bad way to do it. But since this is actually going to come up often in this class, we're just going to go ahead and have it ready to go when we need it. We don't want to have to do this again. It's kind of like deriving the quadratic formula every time you want to use it. That's ridiculous. We complete the square when we have to. We don't complete the square to solve for solutions of a quadratic equation by completing the square. That's ridiculous. We just use the quadratic formula when the zeros are imaginary or irrational. So what I want you to do is to complete what we've been doing with the integration review, and then of course the work on the center of mass, which was kind of fun, if you have to admit that. It just kind of neat to see how these applications work. And now we're delving into the arena of more integration techniques. So we've got a head start on the integration by parts. So go ahead and start working with this once you've completed the others, and maybe just go through a couple of these to wash yourself in the idea of the technique. What I'm trying to do is give you a very simple way to organize the technique, organize the process so you can keep up with the terms. And then plus the 2 passes, well, this is going to be something we're going to do later. I won't share with that now, that'll scare you. But just remember the case where we have the simple integral and the polynomial, how we can actually execute the second pass by staying in the table. That's something I want you to be able to do because it's very clean and very efficient. And that's what we want to do. Integration is taxing. Working with definite integrals, taxing. The algebra can be tedious. With antiderivatives, the algebra can also be tedious, but straightforward. So get practice with this, spend plenty of time with this, and note that we'll do this for the duration of chapter 8, and then we'll move on to our friends, sequences, and infinite series. So thank you for your attendance today. Fortunately, the rain has stopped. We're still getting some flooding, so hopefully you're dry where you are or you're in a safe place. And if I don't see you at office hours, I'll see you next Monday or online with your WebAssign messages. Have a good day.
Thank you. Have a good day.
You too.